Hi everyone, Mike here, and want to try again Fisher's exact test, see what's going on. We start with the word That's Fisher must have been saying that, or as the British would say, when they look at a table like this. So there's a 2x2 table. We're going to call this treatment A and treatment B just to make it easier to discuss. It looks like a 13. So B. And essentially you want to know is there a relationship between the rows and the columns. And that's what a chi-square test is designed to do. It'll work for a 2x2 table, work for bigger tables. The issue here, of course, is we have small cell counts. And so the chi-square test, you're not supposed to use it if any expected cell count is less than 10. So Fisher had this, and he knew the limitation on the chi-square test. And he's like, how do I solve this? And his brilliant idea and the light bulb that went off in his head was realizing that something called the hypergeometric distribution from probability theory fits into this framework, or this framework fits into the hypergeometric probability distribution. Now, if you take a probability class, you'll learn all sorts of distributions, discrete distributions, continuous distributions. And one of the stranger ones, it's based on combinatoric theory, is called the hypergeometric distribution. So we have to introduce it. But we're going to introduce it very, very quickly and just explicitly show why this problem fits into the hypergeometric distribution. So first we're going to look at the hypergeometric, and then we'll try to discuss why this problem fits into it, and then see what the Fisher exact test is doing. So the hypergeometric distribution is a probability distribution, and the setup is as follows. So we know it's a binomial random variable. If you're doing something n times, it's independent. Probability of failure success is the same in each time. That's the binomial. We know when the normal comes into play. This is the hypergeometric. It's a hypergeometric situation if the following holds. The population or set to be sampled consists of n individuals, objects, or elements. There's a capital N there. Each individual can be characterized as a success or a failure, and there are m successes in the population. So there are big N things in the population, little m successes in the population. A sample of n individuals is selected without replacement in such a way that each subset of size n is equally likely to be chosen. You randomly grab n things, n people from this population. The random variable of interest is the number of successes in the sample. And that's called a hypergeometric distribution. And the way you'd find the probability that big X equals little x, the random variable equals a certain value, is the dhyper command with that call. Yeah, a lot of letters floating around here. So let's go over that one more time. But you have a finite population of capital N objects. Within that finite population, capital N objects, there are successes and failures, and there turn out to be little m successes. So bear with me. If there are little m successes, there are going to be capital N minus little m failures, because that adds up to big N. You then randomly draw a sample of size little n. And what do you care about? What's the probability question? The probability question is how many successes are in your sample? And that thing follows what's called a hypergeometric distribution. So Fisher knew this probability distribution existed. And you're like, yeah, so what? Well, he was able to make the connection that table is the hypergeometric distribution. In fact, that table follows the hypergeometric distribution. So let's go back to our original example and see why that's the case. So here's A and B. So what's the setup? We randomize people. They're either on treatment A, they're on treatment B. Then we can see if they're cured or they're not cured. Then we want to see what's going on. So why is this a hypergeometric? So let's go through step by step. This is one. I don't know why one got cut off. The population or set to be sampled consists of 29 individuals. That's the total sum here. So we have 29 total individuals. Each individual can be characterized as a success, well, that's cured, or a failure, uncured. So each individual is either one category, success or failure. And there turn out to be 17 successes, and there turn out to be 29 minus 17, 12 failures. And then a sample of 16 individuals is selected without replacement. So we randomize. So we randomly put 16 in treatment A, 13 in treatment B. We've randomized everyone. And so a sample of 16, that's our random sample in treatment A, are selected. And each subset of size 16 is equal to we chosen. Yeah, we just randomly selected 16 people, so that's absolutely true. What do we care about? The number of successes in our sample. So in this case, we want to know what's the probability we have 13 successes in a sample of size 16. So we have a population of 29. We take a sample of size 16 from the population. Then we want to know what's the probability we have 13 successes in that sample of size 16 from a population of size 29. Whoa, I know a lot of stuff there. What's the probability we have 13 successes in a sample of size 16 drawn from a population of size 29? Freaky! But Fisher was able to see that this table follows the hypergeometric. Now, you're not expected to understand the hypergeometric. You're not expected to know the hypergeometric. It's something you do in 110. We're just trying to show you the connection that Fisher made. And seeing this is what the Fisher.test is doing behind the scenes. But seeing this, then you can see how the p-value is calculated. So from this table from class, if you wanted the probability of observing this table, this is what the call would be in R, where you have to give it how many successes you're interested in the population, how many successes there were, how many failures there were, and the size of your sample. And so you can see on the previous slide what all the parameters are, but this is how you would call it. And that's the probability of observing 13 successes in a sample of size 16 from an overall population of 29, where there were 17 successes and 12 failures. The actual combinatorics of what it's doing is this line here. If you're wondering what it's doing, 29 choose 16 here is the total number of tables possible, the total number of tables that could possibly be created from this data, and then we're figuring out the probability of observing this one table. So we find that the probability of observing this one table is that, pretty small. That's not the p-value, though. The p-value is literally the probability of observing that table or something more extreme, or something less extreme. We actually have to discuss what the p-value is. If we look at this table, it looks like there's a directional test we could run. So we could either run P1 equals P2 versus P1 not equal to P2. That would say that there's no relationship between rows and columns. There is a relationship between the rows and columns. So P1 equals P2 versus P1 bigger than P2, there's a positive relationship. And in that case, we're asking, are they equal proportions, or is P1 bigger than P2? Or we might want to test P1 equal P2 versus P1 less than P2. In this case, if we look at what's going on here, there are 13 over 16 cured on treatment A, but there are only 4 out of 13 cured on treatment B. So it definitely looks like we'd be interested in that. Before we even see the data, there's a belief that treatment A is a better treatment. Treatment B is the standard antibiotic treatment in this case. But there's a priori. We're supposed to set this without seeing the data. We want to point that out. That's important to do. Set the hypothesis before you see the data. But for whatever reason, we want to run a one-sided test. We want to see if there's evidence that treatment A is indeed better than treatment B. So we're going to run this. In general, the one-sided p-values are easier to calculate, and that's why we're doing it. When you do these exact tests, there's a little bit of machinery and mechanics to do a two-sided p-value. So there's a reason for this. It's actually an easier p-value for us to calculate. So the p-value literally is what's the probability of seeing this table or a table more extreme? Well, in that direction, what would be a table more extreme? So a table more extreme would be, see, either 14 cured or 15 cured or 16 cured. Excuse me, we have to stop at 16 because we only saw 16 on treatment A. But this is the observed table, and seeing something more extreme than that would be seeing 14 or 15 or 16. So we can actually calculate everything with the dhyper command. This is the observed value, and then we can calculate the 14, 15, or 16 like that. The p-value is literally just the probability of seeing what you observed or something more extreme. And this is the p-value for that test. And then, no surprise, because this is exactly what it's doing. Oh, it is a surprise because I didn't print it out. I don't want to go back and redo this entire video, so you have to take my leap of faith and actually trust me. Julie's going to be laughing if she actually ever watches this. But yeah, there's a p-value here. I'll just put it in, and you can trust me. It's the same. 0, 0, 8, 4, and whatever. They are actually the same. And you can try it yourself. You have all this data in the lab. Check it out, and you'll see the p-values are exactly the same. So you're doing one-sided, you're actually calculating the probability of seeing that table or something more extreme. So you're doing a 13, 14, 15, or 16. The two-sided is actually a little bit more complicated to calculate by hand, because in that case, we're talking about being more extreme on the right-hand side or the left-hand side. So you'd have to actually calculate more probabilities to get the two-sided p-value. A cheaper way p-value is just to go and double the one-sided p-value, but there are actually more advanced ways to do it than just doubling the one-sided. So if you actually run Fisher.test by itself with no alternative here, it's doing the two-sided, it's calculating the two-sided p-value correctly internally. If you do the one-sided, you can always check if you wanted to the calculation that R is doing with Fisher.test by just doing it by hand. And here, if you actually run it out, you'll see they do agree exactly. So I hope that helps a bit about what Fisher's is doing. The big idea that Fisher had in the light bulb moment was realizing that this setup here followed what's called a hypergeometric. We had a population of 29. We had just successes and failures going on. We knew the number of successes, 17. We knew the number of failures, 12. We're taking a sample of size 16. So we're going to look at treatment A, and we're taking a sample of size 16, and we want to know how many successes were in that sample. And that's the probability of that table. And then the p-value is literally the probability of observing that table or something more extreme. Again, using the hypergeometric, we can find it. It's one of the more unusual tests because it uses a lot of probability theory that we have not seen whatsoever, and you would see in 110, because they do a lot of this combinatoric stuff in 110. It's a useful test to know, and especially you want to use it when you have small sample sizes. Hope that helped a little bit, and hope you're having a great day. Thank you.